Right. Thank you, sir, for that kind introduction. And thank you all of you for coming here at 10 a.m. in the morning for my talk. So, let me get started. So, today I'll be talking about my work that I've done during my PhD, and it's about fast and scalable algorithms for intelligent routing of autonomous marine agents. So, autonomous marine agents, like the ones that you can see in these pictures, these can be surface autonomous vehicles or underwater autonomous vehicles. They are rapidly going in demand because they're very useful in missions like, let's say, data collection for surveillance and security operations or resource exploration. And no matter what the mission at hand be, we want these autonomous agents to take autonomous decisions while traveling from some point A to some point B in oceanic environments. And we want them to maneuver optimally. That is, we might want them to minimize their travel time or their energy consumption or the risk involved. And we want to do this because we want to minimize the operational costs for these agents. And so that brings me to the problem statement itself. So let's say that we are given this spatio-temporal domain, and inside this domain, we are given some starting location x naught and a destination location xf in the presence of a stochastic velocity field, that is v. So think of ocean currents when you think of v. And we have an objective to optimize. So, for example, you could want to minimize the travel time from x naught to xf, and maybe some constraints like a limited mission time and limited battery. And so the key question is, how should this autonomous agent route itself optimally to meet its objectives and constraints? And so to answer this, we have to answer some other key questions. For example, what are some good path planning and onboard routing methods for stochastic dynamic environments for these agents? What are the limitations of those methods and how do we overcome those limitations? We do propose some methods from our end, and we discuss in this work or the series of works the advantages and useful applications for those proposed methods. So before I actually move on to those proposed methods, let me talk about a bit of the literature on path planning. There are graph-based methods like Dijkstra and A-star that are better suited for, let's say, deterministic and static environments. Then you have Hamilton-Jacobi level set methods, which actually work as follows. They start out by computing these reachability fronts. And once these reachability fronts reach this target location, you do a simple backtracking to get a time optimal path for this particular problem, let's say. But then these methods are more suited for deterministic and dynamic flows, but handling stochastic flows can be a bit computationally expensive. Then we have MDP, that is Markov decision process, and RL, reinforcement learning based methods, which are actually quite popular for planning in stochastic environments. But often they're used with some simplifying assumption and can still be computationally very expensive. For example, in this 2018 ICRA paper, the author has planned a path or found an optimal solution for this particular oceanic environment right over here. Uh, and in spite of using a Gaussian to account for the uncertainty in this deterministic setting, it took around 13 hours to compute an optimal policy for such a problem. So it's pretty expensive. And then finally, of late, we have some deep learning methods. Deep learning methods either work by approximating some component of these existing methods. And another way to go about it is for deep learning methods to cast the path planning problems as sequence learning problems. But the thing is that these methods can lack interpretability. In the work that we propose, we narrow our focus down to MDP-based methods and deep learning methods. But then the philosophy of our approach is that we should try and address the challenges of these methods. That is, for MDPs, we do not want to use any simplifying assumptions, and we want to address the computational expense. And for deep learning methods, we want to address the lack of interpretability. So, as I said, the methods that we've narrowed down onto are the Markov MDP-based methods and deep learning methods based on sequence modeling. Now, no matter what approach we used, there are actually two cases when it comes to the routing of these vehicles. We could either do offline planning. That is, let's say we already know how the velocity field is going to change with time. We'll compute optimal solutions a priori and then let the agent act in the mission. Or we could do onboard routing. That is, let the agent make decisions in the mission itself based on environment measurements and observations at it on the go. Anyways, so coming back to the two approaches, I already told you about the limitations of both these approaches. So in case of MDPs, where computational expense is an issue, we try to either approximate or accelerate computing solutions for the MDPs. And when it comes to deep learning methods, our aim is to build interpretable transformer models that can help us predict or help the agent predict optimal action sequences in these oceanic environments. So based on these two approaches, I have two sets of works. So in the first set of works, there are three works based on MDPs, and then I have the next two ones based on deep learning methods, and I'll go over each one of them in time. So before I actually start with these works, I'd like to give you all a bit of background based on like what MDPs are and what, let's say, some other concepts that will help us all to understand the work a bit better. So I've been talking a lot about MDPs. So essentially an MDP, a Markov decision process, is defined by a set of states, actions, transition probabilities, and rewards. So imagine this is an MDP in the form of a grid world where your agent can be present in one of these 9 states at a given point of time. And in each of these states, it can choose any one of the actions of either going upwards, rightwards, leftwards, or downwards. So essentially, it can choose a sequence of actions and traverse a trajectory to reach the terminal state. Then we have the state transition probability that encode the stochasticity in the environment, which says that if you're in state S and perform some action A, what is the likelihood that you end up in any of the other states? And finally, we have a reward function that is an incentive for the agent. It's a scalar incentive. For example, if you're in this state and choose to go up, you get a -1 reward. And if you choose to go right and hit a wall, you get a -2 reward. In any case, what we're interested in is to find a policy, and in fact, an optimal policy, where a policy is defined as follows. It's a mapping from states to action. And figuratively, it can be imagined like this. So this is a policy which tells the agent what action it must perform in any given state. And so let's say if the agent was supposed to start in this blue location and traverse and act according to this policy, then it would traverse this particular trajectory. Now, based on the rewards it gathers in the trajectories from a given starting position, we define something called the value function. So this example right over here, the numbers filled up in this grid, this is an example of a value function. And our aim at the end of the day is to compute optimal value functions and the corresponding optimal policy for that optimal value function. The way we do it, well, briefly, we use dynamic programming algorithms in order to do this. And we can always compute optimal value functions and thus optimal policies if we have a priori given to us state transition probabilities and rewards. Another way to go about solving MDPs is to use reinforcement learning algorithms. One such algorithm is Q-learning. And here in Q-learning, the idea is to learn these optimal Q values from trajectory information that could be collected either by exploring the environment or from some log data. So I hope this gives us all a brief intuition as to what MDPs are and how we use dynamic programming and RL. The next topic that I'd like to talk about is the decomposition of flows or how we use them. So on the right over here on the top movie, you see a double gyre flow. So this double gyre flow is essentially an oceanic flow, which is in the form of two gyres or vortices. The gray lines represent the gray streamlines represent the direction of the flow, whereas the color represents the magnitude of the flow. And essentially, so this is a dynamic flow. And at any given time step, I can decompose this flow into a mean flow, a set of dominant modes and corresponding coefficients. And the idea is that this flow at, let's say, time step t equal to 0 can be expressed as a sum of mean and a weighted sum of the modes, where the weights are nothing but these coefficients that we've already pre-computed. So the idea is that for a given set of coefficients, I have one sample of the flow. And let's say if I want another sample in this orange box instead of this green box, so this orange box is a new sample of the flow, I would just have to change the coefficients and I'd get a new sample. Essentially, doing this decomposition, it helps us with two things. First, it helps us save a lot of memory. And the second, it gives us a representation. So the vector of phi's over here gives us a useful representation for representing this entire flow all in all. So yeah, these were some basic concepts that I want you all to be familiar with before I actually move on to the work. So first, I'd like to start off with MDP-based methods, right? Among the MDP-based methods that we proposed, the first work that I want to talk about is the physics-driven Q-learning for onboard routing. So here the specific problem statement is as follows. You have the autonomous agent P in this environment that has to go from X0 to XF. And we want to compute an optimal policy that minimizes the travel time for to go from X0 to XF. And we want to dynamically update it as well. So this requires an in-mission measurement of the velocity field V. and we'll have to do some data assimilation to get a posterior estimate of the field. And then based on that new estimate, we would like to update the policy continuously. So that is the overall idea. Now, in order to solve this problem, we've set it up as a Markov decision process. The state space is a discretized 3D spatio-temporal grid, which looks something like this. So a state is defined by the spatial coordinate and the temporal coordinate. Then you have the action space, which is a discretized set of headings. So you have, let's say, 8 discrete headings over here for the agent, 8 different directions. And the velocity f is of the agent is supposed to be a constant. Then the one-step reward is defined as, you get the agent is penalized with a constant negative term for every action that it takes in any state. So now we want to compute the optimal policy. Well, we can compute it, as I said, using dynamic programming methods, but they do give us the exact solution, but they can be very expensive to compute. So how do we go about it? Is there a feasible alternative? Yes, there is. We can try to approximate the optimal policy. So the way we are trying to approximate the optimal policy is through this modeling framework. First of all, we model the environment, that is where the environment where the agent is going to go out in the ocean. So we try to get some compute some n realizations of this velocity field, n samples of the stochastic velocity fields. For each of those n samples, we employ the Hamilton-Jacobi level set equations to compute optimal trajectories for each of these samples. And if I happen to club all of those trajectories together, what I'd get is a distribution of trajectories that looks something like this. After that, finally, the idea is to use reinforcement learning algorithms like, let's say, Q-learning, so that we can learn or estimate the optimal Q values from the trajectory information. And then we use the dynamic programming solutions as a benchmark for our model. So this is how the overall algorithm works. The first phase is actually a transfer learning phase, which happens offline, wherein we first compute the n realizations of the velocity field. For each of these realizations, we compute optimal paths and get a distribution of optimal paths like this. Then for each of these paths, we do some pre-processing. That is, we try to find out what sequence of states and actions and corresponding rewards should be processed so as to traverse a given optimal trajectory. So that gives me a sequence of S, A, R, and next state S dash. And if I do that for all the trajectories in the distribution, I end up with an experience buffer that looks like this. Now, essentially, I'll have to, the idea is to use this experience buffer to update my Q values using the Q learning update equation. And from that, I can compute my initial policy pi1. And this all of this happens offline. In the online phase, when the agent has to go out into the ocean for a mission, initially it will start off using the policy pi1. And let's say that somewhere down the line, it's in this location. So the next action that the agent is going to perform is based on the most recently updated Q values. At this point of time, it's going to take some measurements from the environment and compute a posterior estimate of the field. In this posterior estimate, the idea is to for the agent to simulate some future rollouts. That is, essentially, it's going to try out different action sequences in simulation and try to see whether some action sequences would lead to the target a bit faster. So in this case, the green trajectory happens to reach a bit faster, and the agent decides to go towards or in the direction of the green trajectory. It takes a step towards the green trajectory and updates the Q values once again. So this happens in loop, and the agent reaches the target location at the end. Now, based on this philosophy or based on this methodology, we have this experiment where for the double jar flow scenario, we've compared how our trajectories for our QL-based model compares with the benchmark dynamic programming method. So we see that qualitatively, of course, they look very similar, and quantitatively, we'll see that the amount of time required for the agent to reach the target for our case is 13.1 days compared to 12.6 days for dynamic programming, which is a minor trade-off in performance. But then, as far as the compute time is concerned, our algorithm takes roughly 11 minutes compared to the 90 minutes it would have taken you to use conventional dynamic programming approaches. So this gives us a roughly 8 times speed up when it comes to computing these optimal policies. So in conclusion, at least for this section, we talked about a physics-driven Q-learning approach to compute optimal policies and do onboard routing, where the first phase of the algorithm involved learning an initial policy from the Hamilton-Jacobi trajectories using a Q-learning equation. and then dynamically updating that policy on the go in the mission using a future rollout scenario. And we saw that we got speed ups of roughly up to 8x with a minor trade-off in performance. Now, so this is one work. Now I'd like to move on to the next piece of work. Up till now, we tried to approximate the optimal policy, but now we're going to move on and try to accelerate computing the optimal policy. So the way we do that is by using GPUs. And so the specific problem statement for this piece of work is as follows. Once again, you have the autonomous agent that has to travel from x naught to xf in the presence of the stochastic velocity field. But then we have added a bit more complexity to the problem by saying that there is an additional stochastic dynamic scalar field as well, and you also have some dynamic obstacles. So by a dynamic scalar field, I mean something like, let's say, the radiation from the sun. And so imagine in these series of pictures, the yellow region is a sunny region and the red region is a cloudy region. And over time, the cloud cover moves from right to left. So this is what I mean by an example of a scalar field. And so essentially, and an agent with the capability of harvesting solar energy can try to stay in the sunny region and collect energy if it's trying to minimize its energy consumption. Anyways, the problem is once again cast as an MDP. And we can, of course, solve the MDP exactly by using a dynamic programming algorithm like value iteration. And the equation for that is given over here. But then there are two computational challenges. First of all, if you want to do value iteration, we just have samples of the velocity field. We must first compute this P, that is the state transition probabilities, which in itself is a big task. And then we also must solve for this value iteration algorithm, and that itself is computationally expensive. So the idea is to use efficient GPU accelerated algorithms to accelerate both these phases and hence get optimal policies in a much faster, efficient way. So the reason we use a GPU, the motivation behind it is, well, first of all, the transition matrices would be sparse. And the reason behind that is that if you're in some state S, then you can only land in some nearby states S dash, perhaps in this green region, and not anywhere arbitrarily in this entire grid. More important is the fact that model building, that is computing state transition probabilities, is embarrassingly parallel. What I mean to say is that if I want to compute a transition for this state and this action versus this state and this action, these computations are absolutely independent of each other and can be done in parallel. And this independence holds across different samples as well. And as far as the value iteration algorithm is concerned, there is a parallel version of it called the sparse value iteration, which we tweak slightly to make it work for our purpose. The major challenge, although, is the fact that GPUs can come with limited memory and compute resources. And so a lot of work went into trying to handle these problems. So one solution was to try to use a reduced order velocity field that I talked about a bit earlier. That is, use a decomposed velocity field, which saves a lot of memory. Then we use a neighboring subgrid idea, wherein when we're trying to compute what possible S dashes can I land to while computing the transition probabilities, I only need to see a neighboring subgrid from a particular starting initial state. So that I just need to put my focus in on this green region and not worry about the entire white region. Finally, we also prove that as far as the stochastic scalar field is concerned, mathematically, we can prove that the mean of the scalar field is sufficient for our problems. It's a bit involved, so I'll skip over that part for now. And finally, a lot of work went into the implementation of some efficient kernels for the algorithm. Just to give you an intuitive idea of what's happening inside the GPU, so this is a schematic that shows that. So imagine that you had some velocity fields, some samples of the velocity fields like this, and I stacked them one on top of the other. So you see that stack something like this inside the GPU. The X and Y axis are stand for the spatial axis, and the Z axis is the sample or the realization axis. Now, each cell in this block over here is a velocity field, or it's a velocity. And so the idea is to build a block of threads that will take care of each of these velocities and the transitions that they induce. So all of these threads in this block are going to work parallelly and compute all of those transitions parallelly. And essentially, we gather all of that information from all of that threads to compute average rewards. And once again, all the information from all of these threads to get the state transition probabilities in a neat fashion. Suffice it to say that once I have computed all of this, I get my P and R, that is the state transition probabilities and the average reward. And now I can finally use these in my sparse value iteration algorithm to compute the optimal policy at hand. So let's say I've already done that. So right now I want to show you some applications or some results of this work after having computed the optimal policies. So I have three scenarios over here. In scenario one, I'm optimizing the expected arrival time of the agent. So what we see over here is the evolution of a distribution of trajectories across time. And we see when we were trying to optimize time, the agent sort of quickly moved towards the target while avoiding the obstacles across all realizations. On the other hand, when we are trying to optimize the expected energy consumption, we see that the paths taken by the agents are now more curvy in the sense that they try to utilize the flow of the environment and then reach the target. So they do end up taking more time, but then the energy consumed is much less in this case. And finally, perhaps a more interesting case is when we try to optimize the net energy consumption. So the agent in this case first moves towards the left, tries to remain in this sunny region for as much as possible. And once it's no longer feasible to do so because the cloud covers are coming towards the left, it will quickly move towards the target location while avoiding the obstacles at hand. So all of these experiments were done for a grid size of 200 cross 200 cross 200, which are pretty big compared to most of the things that you'll find in recent papers. And the actions, that number of actions that we used for 32. So in terms of runtimes, including model building and the solving time of the MDP, all of this was done in 7 minutes for a much larger grid size. And if we compare it to some papers, let's say, which use simplifying assumptions like having Gaussians to account for the uncertainty in the flow, for much smaller problem sizes with sequential approaches, it takes about 13 hours. So you've come down from a matter of hours to a matter of minutes, and that really enables us to deal with some real-time applications. As far as some runtime analysis is concerned, so let's say we wanted to see how the speed up, what kind of speed ups we get as we scale with the number of, as we scale with problem size based on the number of states. So we see that we can get speed ups ranging from 600 to 1000, depending on the kind of GPU that we're actually using. So that was GPU accelerated path planning. Next, we moved on and made things a bit more complicated in the sense that now instead of wanting to optimize for one single objective, we want to optimize for multiple objectives. So for example, we might want to optimize for both the expected mission time and the expected energy consumption. And the way we go about it is to use scalarized rewards. So that is take a linear combination of the rewards for minimizing the time and the corresponding rewards for minimizing the energy consumption. And so the idea in this case is not just to compute one policy, but to compute a series of policies so that we can get something called an optimal Pareto front or a Pareto optimal front. So this Pareto optimal front essentially tells us or gives us an idea of about the trade-off between the two objectives. So for example, how the average time required would vary with the average energy consumption if I chose different values of alpha. So each point in this plot is actually a solution of an MDP and gives you the time and energy required if you were to choose a given value of alpha. And so the point of this work is to compute these Pareto optimal fronts by building and solving MDPs for multiple values of alphas. And since each MDP solve is a matter of minutes, this can be done very efficiently. So we use our end-to-end GPU planner that I discussed in the previous work. And then at the end of the day, allow the operator of the AUV to choose a value of alpha based on his time and energy budgets. Then, as far as applications are concerned, one application, once again, is to see how, if we try to optimize, let's say, both time and energy. So if I put alpha is equal to 0, we're essentially optimizing simply just for time. And we see that the agent would just quickly reach the target location while avoiding the obstacles. If we optimize for just energy by putting alpha equal to 1, we once again see very curvy paths, avoiding the obstacles, trying to stay in the sunny region and reaching the target. And if I put an alpha value of 0.3, something intermediate, we see that the behavior of the trajectories is also intermediate in nature. Another interesting application is the shipping channel problem. Over here, what we're trying to do, the agent has to go from point A to point B. At the same time, it must cross this shipping channel wherein a lot of ships move from, let's say, left to rights at regular intervals of time. And we would like that this agent does not collide, or we would at least want to analyze whether collisions are possible or not. So what we do is that for different starting values of the ships, starting locations of these ships, that is P naught ranging from 0.1 to 0.5 in this case, we compute these optimal fronts. And we can do an analysis as follows. For example, let's say in this region, we see that if you have alpha values greater than 0.3, you're not actually acting Pareto optimally, meaning that you're using more time and more energy, and hence maybe you should not operate at these alpha values at all. So we can tell the operator that, the alpha values that you should be operating at are range between 0 to 0.3. Now, the point is that this kind of an analysis with conventional methods would take a lot of time, because you would be solving multiple MDPs for one p-value and then do the same for multiple p-values. And it would take up to 43 days, let's say, uh, if you used conventional methods. But with our GPU accelerated algorithm, what we can do is to do this analysis within 12 hours. So it means that if you want your agent to go out on a mission today, you can use today's velocity field information to plan for these paths and do a suitable analysis, which otherwise would not have been possible. So in conclusion, for this segment of the work, we've developed an efficient GPU accelerated path planning solver that handles dynamic obstacles and stochastic scalar fields as well. And we used a GPU, exploited the fact that, model building was embarrassingly parallel, and achieved speed ups up to 600 to 1000 times. And we also extended that to the multi-objective settings by using scalarized rewards and quickly computing optimal operating curves. And we could solve nice problems like the shipping channel problem. A quick caveat is that, onboard routing can also be done through this, uh, as long as we can do this through repeated planning in the mission, as long as we have the compute resources on board. So now this brings me to the end of the MDP-based methods. Now I'd like to move on to the next segment, that is our sequence modeling-based deep learning methods. So among these, the first work is the intelligent onboard routing with decision transformers. So the problem at hand is as follows. The agent has to go from x0 to xf in the presence of the velocity field once again. But now, at any given point of time t, the agent must predict the optimal action at, conditioned on the fact that it has already traversed this YT already. So essentially, it has to make optimal actions on the go based on in-mission measurements that are encoded in the historical trajectory YT. The challenge over here is that since it is onboard routing, the decision making has to be fast. And we also want our agent to be able to handle multiple targets, but maybe I'll not talk about the multiple targets today. So the key idea behind solving this problem is as follows. We model, first of all, this problem as a sequence modeling problem and solve it using a decision transformer. I'll talk about what a decision transformer is. And then finally, we try to learn optimal actions from expert trajectories. And I'll talk about what expert trajectories are too. So over here, this is a picture of a decision transformer. So essentially, it's a decoder only kind of transformer, which has a causal mask inside it. And it is auto-regressively trained on a sequence of returns, states, and actions that I get from an MDP setting. So over here, the state, by state, I mean the spatiotemporal location of the agent at any point of time. And by action, I mean the heading of the agent. And returns are returns that it gathers on the way. So this model is auto-regressively trained. And the key thing to notice over here, that for such a model, the action predicted at time t is naturally conditioned on all the previous tokens. That is the historical sequence of states and actions. And that lies in perfectly with what we want to do as well, because we want to predict actions at any given time t conditioned on a historical trajectory that we've observed so far. And so that is why we move ahead with the decision transformer to solve this onboard routing problem. A quick note is that the sequence of state, actions, and next states also encodes what local velocity the agent has observed, and that actually helps the agent infer what kind of realization it is in. I'll show some results regarding that in a couple of slides. So now that we know, okay, so the idea is clear, I hope. Now, as far as the data set is concerned, the velocity fields that we use over here are double gyre velocity fields and also highway fields. So highway fields are hypothetical fields where the flow would be restricted to this band and either move towards the right or towards the left. And we use both these kinds of fields in the experiments that I'll talk about in a bit. And as far as expert trajectories are concerned, these expert trajectories that are used to train the model come from either the Hamilton-Jacobi level set solver that I had talked about earlier, or they can come from our dynamic programming solver itself. Right? So we can have paths from our dynamic programming solver that and use these paths to train the model as well. So now coming to the overall methodology, as I said, we're using an architecture based on the decision transformer. Since it's a natural counterpart to what we want to do. A tweak that we've made is that the first token we've put in as a target location itself, because we want that the action should be conditioned on where the agent is headed in the first place. So that conditioning is done. The loss that we're using is a simple MSE loss over the actions. And so this is how the overall flow of information happens, or the computation happens. First, we have our expert trajectories coming from a solver. Then we do some pre-processing and figure out what are the sequences of state, actions, and rewards that would lead to these trajectories. And if we gather all of that, we end up with a logged experience or an experience buffer once again. We append the target token to all this experience buffer and use this data set to learn autoregressively a model based on our decision transformer. So the advantage of our approach is, like, first of all, we do have multi-target routing capabilities, but in interest of time, I'll skip over that. And that it really generalizes to some unseen environments, and I'll talk a bit more about that in the upcoming slides. As far as applications and results are concerned, we have done a lot of experiments and showcased 8 scenarios over here, out of which I'll discuss a few. So what we've done is that we've trained on some kind of flow, and we've tested on a similar or a different kind of flow. And we've compared the performance in terms of the expected arrival times, that is how much time it takes for the agent to reach the target. And we've compared our model, the decision transformer based model, to the expert trajectories that are coming from these solvers. So let's see some scenarios. On the left-hand side, what you'll see is the ground truth data, that is trajectories coming or predicted from the solver. And on the right-hand side, you see the trajectories that are predicted by our model. So in scenario 1, it was trained on double gyre scenarios and tested on the test set of double gyre scenarios. And we see that both qualitatively and quantitatively we're acting near optimally. A similar thing is observed when we use like train and test in mixed highway flows. So once again, qualitatively and quantitatively, we see that we get very similar results. And the reason why we're getting very similar results or good results is because of the fact that these agents can essentially learn to infer what sample of the flow they're present in, and that helps them to perform the correct action sequences. A quick note, on the left-hand side, what you see, all the plots on the left-hand side come from a planning algorithm. That means when these trajectories were computed, we had a priori information of how the velocity field was going to change with time. But then the ones on the right, they come from an onboard routing algorithm. That means these trajectories were made by taking decisions on the go without idea of how the future velocity is going to change. So that makes things a bit difficult in terms of predictions. Now to talk about some generalization capabilities. Here in scenario 5, once again, we trained and tested in the mixed highway setting. But the interesting thing is that now we start outside the flow. So the agent is essentially present initially in this part where there is no flow, and hence there is no signal for the model to compute optimal actions because there is no velocity field. So initially the agent starts going upwards because that is the average of what it has seen in the training data set. And it will go upward until it actually hits the part, this band of the flow, where it actually gets the velocity signal. Once that velocity signal comes, the agent is now able to sort of infer what realization it's present in and start taking appropriate actions accordingly. And we see that it's acting near optimally. It does reach the target in all locations. And the key point to notice over here that by the time the agent reached this place, the history that it is conditioned on was never present in the training data set. So it's sort of a new unseen scenario in that sense. And in spite of that, the agent was able to reach the target location and generalize to these unseen scenarios. Then in the next case, what we've done is exclusively trained on left highway settings and tested on right highway settings. That is to say that we've trained on trajectories that go right first and then reach the target, but then tested them on trajectories that should actually go left first. And the results that we get is that, of course, we are not acting optimally at all, but but that's reasonable because it was never trained on such data. But in spite of that, all of the trajectories are reaching the target, which sort of hints at a good potential for the agent to or the model to extrapolate reasonably well to these unseen scenarios too. And finally, we tested how our model, whether our model is robust to noise or not. So during train time, it was all fine. But during test time, we additionally added this extra noise that changed the transitions a bit. So in spite of adding this extra noise, we see that the agent once again reaches the target. Once again, the same fact holds that the agent at a given point of time would be conditioned on a trajectory that was actually not present in the training set. And so it's able to generalize reasonably well to such noise as well. And it's basically robust to noise up to a certain extent. So the results that we're getting are pretty decent. But then we want these results to be a bit interpretable too. We want to know why we are getting such results. And to try to explain that, what we've essentially done is to take the attention heat map of our transformer model, and then we took out the appropriate pixels from this heat map and plotted them onto these trajectories. So essentially, in this figure, what you're seeing, the red color denotes how much attention was paid while taking an action at that particular time in that trajectory. So the darker it is, the more attention was paid. And of course, the blue color represents the magnitude of the flow. And what we see is that most attention was paid by the agent in those parts of the trajectory that exactly overlaid with the critical regions of the flow. These regions of the flows are those regions that are high in magnitude. And that ties in very well with the intuition that if you're in a critical region of the flow and if you happen to take a slightly wrong action, it will have a more adverse effect on the expected arrival time. And so that is exactly what we see in this observe in this heat map too. And that helps us up to a certain extent explain why these models are working well. So in conclusion for this work, we developed a transformer-based model where the agent essentially learns to infer what realization it's present in and act nearly optimally. Uh, it shows good generalization capabilities to unseen environments, robust to noise up to a certain extent. And of course, the attention mechanism attends more to those actions that are taken in the critical regions of the flow. And at the end of the day, since we want to do onboard routing, decision making in this case is pretty fast because it's just a simple forward pass through the network at some intervals of time. So that brings me to the end of that work. And now I'd like to move on to the last piece of work, where we try to do path planning, not onboard routing, but simple path planning with environment encoders and action decoders. So now the problem statement for this work is as follows. The agent has to go from x naught to xf in the presence of this velocity field v, but there will be obstacles in the way as well. And it has to, and the idea or the problem at hand is to compute an optimal action sequence from a sequence of environment information. And so the key idea over here is to simply cast this problem as a sequence to sequence translation task. So over here, the environment representation, so essentially we're going to go from environment representation sequences to optimal action sequences through an encoder decoder model. A valid form or a valid representation of the environment can actually be the do coefficient fields do coefficients for the fields that I talked about earlier when I was talking about some background. And finally, the idea is to try to generalize across different flow and obstacle configurations so that we don't have to call upon expensive solvers over and over again. So as far as the dataset is concerned, we use a double gyre flow scenario and a scenario of the flow past a circular island. And as far as expert trajectories are concerned, just like the previous work, we use either the level set equation trajectories or trajectories from our dynamic programming solver. So this is the overall methodology. We develop a path planning translation transformer, which is essentially an encoder decoder kind of model. So the encoder would process this environment information, and that environment information is present in the form of environment embeddings, and I'll talk about what these are. And then the decoder would decode that information and predict optimal action sequences. So this is how the overall flow works in this case. So let's say we have a velocity field like this, dynamic velocity field. As I said earlier, a valid representation of this field is essentially a vector of its coefficients that we can get by decomposing it. So one given vector. So for example, let's say if you're talking about this scenario right over here of a dynamic flow path cylinder flow. So the overall environment embedding vector consists of two parts. One part is for the flow itself, and that can come from the two coefficients that I talked about. And then the other part of the environment embedding vector sort of embodies the location of the obstacle in itself. So these two information together make up a representation of the entire environment. And then we use a sequence of these environment embeddings that are fed into the encoder. Now, as far as the actions are concerned, for this dynamic flow, we call upon our old solvers and get our expert trajectories, and then pre-process these or process these expert trajectories to extract out the sequences of actions that would lead to these trajectories. And so we have a sequence of environment embeddings and we have a sequence of actions, and this encoder decoder model is simply trained on this data. Now, as far as how we train, we come up with a variety of different configurations. So for example, this is a dummy example where we have two different realizations of the flow and three different configurations of the obstacle. So we actually train on a large number of flow and obstacle configurations. And then we test on some new realizations and obstacle configurations to test the generalization capabilities of the model. So essentially what we do over here, once again, we evaluate the performance based on the expected arrival times and the success rate as well. So success rate is what percentage of time were you actually able to reach the target. And the comparison is done with both the expert trajectories and some other models like encoder-based models and just simple feed-forward networks based on behavior cloning. And we see that more often than not, our model does, in terms of success rate, perform a lot better than these other models. Of course, there are some hard cases where the obstacles are present in the region of critical flow. So, for example, you'll see that this obstacle is present in a region where the flow is very strong. And so sometimes what happens is that the agent, when it's very close to the obstacle, if there's a very slight error in the prediction, it may just bump into the target, which can sometimes in these cases lead to a hit in the success rate. But other than that, the model performance qualitatively seems very similar, very good to the ground truth, very similar to the ground truth, and hence it's sort of able to generalize up to a decent extent. A nice experiment over here is this scenario 4, flow past a circular island. Over here, what essentially we've done is that we've colored or indexed the trajectories that are going north of the island with green and the southern ones with yellow. And we've kept a track of those realizations and samples. And we've plotted them once again during predictions. And we see that the green, even during our predictions, the green trajectories are where the greens were supposed to be, and the yellow are where the yellows were supposed to be, which sort of tells us that the agent is once again able very correctly and nicely able to realize which or infer which realization or sample it's present in. So in conclusion, for this work, we developed a path planning translation transformer for path planning applications by casting the path planning problem as a sequence to sequence translation task. We used an encoder decoder architecture where the encoder processes environment embedding sequences and the decoder predicts action sequences. And we achieved good generalization over unseen floor scenarios and obstacle configurations. And once again, in this case as well, the decision making is fast because it's at the end of the day a simple forward pass through the network. So to quickly summarize what I've talked about today, the key contributions of my work are as follows. I talked about two categories of works. The first one based on Markov decision processes, wherein the major challenge was to address the computational expense. In those series of works, the first work was about this physics-driven Q-learning, where we developed a physics-driven Q-learning algorithm for approximating the optimal policies and achieved 8 times speed up compared to the conventional dynamic programming methods. Then we went on to compute exact policies, but then accelerated them using a GPU. We made our own MDP solver and we accelerated building the MDP models, and we computed the optimal policies and achieved speed ups up to 600 times compared to sequential CPU implementations. And then we extended that to a multiple objective setting and accelerated computing the operating curves or these Pareto optimal fronts for multi-objective missions. Then I moved on to deep learning methods, where we developed a decision transformer based method for onboard routing purposes that shows good generalization in unseen environments. And of course, decision making there was very quick because action predictions were just a forward pass through the network. And then finally, we moved on to our path planning translation transformer, which was an encoder decoder kind of model, which cast the path planning problem as a sequence to sequence translation task and then showed good generalization over unseen obstacle configurations. And of course, all of these results in terms of deep learning models were interpretable through the visualization or novel visualization of our attention scores. So that brings me to the end of this talk. These are the publications that have come out of my work. Uh, Thank you all for coming for this presentation. If you have any questions, I'd be happy to answer them.
All right, thanks, Rohit.